All right, as we review for the test tomorrow, we want to take a look at that math handout that I gave you on Friday, or if you're Grace or Nick, the handout I literally just handed to you. Let's take a look at these together, and kudos to Olivia. Didn't have to do it, still took some time to do it, so hopefully that'll really benefit you come test day tomorrow. Problem number 1 says calculate the pressure in a 14.5 liter helium tank if it contains 95.5 grams of helium at 298 Kelvin. It wants us to find, class, the pressure. It gives us liters, which is volume. It gives us grams, which is mass. But mass is always related to the number of moles. And it gives us 298 Kelvin, which is temperature, right? What equation would we have to use to solve problem number 1? It's been a little while. It feels like forever. Tyler? PV equals nRT. We're like, oh, wow, that formula, it's been a long time. Yes, it has been. All right, so PV equals nRT is our formula, and it says calculate the pressure. So to get P by itself, I have to divide both sides, class, by the... Well, I want to get the P by itself, by the volume, right? So we're going to have the number of moles times the R times the T over the V. Now this R, what is the R, class? 8.314, right? It's that universal gas constant. So we have a number of moles times that 8.314 liters times kilopascals over Kelvin times moles. T, of course, is the temperature. And the V down here is the volume. Well, no question at all about the volume. It comes right out and tells us what the volume is, class. 14.5 liters. Like it when things are easy. And by the way, the liters will cancel. The temperature we don't have to wonder about. They tell us 298 Kelvin. And again, that allows the kelvins to cancel. We know the pressure is going to be the kilopascals. It's just the moles have to cancel. And they don't tell us the number of moles. Instead, class, it says we have 95.5 grams of, what is it? Helium? All right, so we flip to the back cover of the book and we look up helium's number. What is helium's atomic mass number?
4.0026.
4.0026?
Yes.
Is that for H2, HE2, or just HE?
That's just HE.
Okay, they have four decimal places. Okay, all right, so 4.0026. But we have HE2, so we got to multiply that by 2, class, to get
8.0052.
All right, that's how many grams are in a single mole. That makes sense? One molecule would be as many unified atomic mass units, but a mole is that many grams. Well, I've got way more than 8 grams, don't I? I've got a whole bunch of moles here. What do I do to figure out how many moles I've got? Divide. Or you could say take the 95.5 grams you've got, put it over 1, and multiply, remembering that a mole is 8.0052 grams. We'll put the 8.0052 grams on the bottom, with the mole on the top, and allow the grams to cancel. Basically, you're dividing, right? So whichever method works for you, you use it. That's going to be a lot of moles. That's going to be well over 11 moles. How many moles do we get?
11.9.
Somebody else get the same thing, 11.9? 95.5 divided by 8.0052?
Yep.
11.9, I'm assuming ... and it keeps on going. All right, that number of moles cancels with this moles. And so there's our kilopascals for our answer. We're going to take that 11.9, blah, 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 times 8.314, times the 298, divide away the 14.5, and that gives us what pressure? What did you get, Olivia?
2,040 kilopascals.
2,040 kilopascals. That's rounded to the 3 sig figs? All right, I'm assuming it didn't come out evenly, there's no way. But 2,040 kilopascals, I mean, that's some pretty intense pressure. Well, yeah, we've forced a lot of helium into a tank that we can use to blow up balloons. So of course it's gonna have a lot of pressure in there. I think that's actually fairly accurate, if I'm not mistaken. Questions on this? You already did it, you got it correct, awesome. The rest of you didn't do it in advance. Do we understand it now? Yes, ma'am.
So for the number of moles, you can't take the 95.5 what?
Well, 95.5 grams we use to tell how many moles we've got. Okay. So first thing we figure out is, well, what is 1 mole of helium? Well, 1 mole is only 8 grams, basically. So if we have 95.5 grams, divide that by the 8 grams it takes to make a mole, And when we divide, we get 11.9, almost 12 grams. We have almost 12 grams of helium, or 12 moles, excuse me, of helium, and then just multiply everything out from there. All right, good. Other questions on this one? Let's take a look at the next one here and read that for us while I erase. Tyler?
A simple oxygen gas collected over water at 28 degrees Celsius occupies 0.64 liters at an atmospheric pressure of 101.4 kilopascals. How many moles of oxygen were collected?
What happens when we collect gas over water, class?
Vapor pressure.
The vapor saturates the air as much as it possibly can at that given temperature. And so there's vapor pressure, not because of the evaporation condensation reaching equilibrium, but just because you were literally forcing gas into water and displacing water, it's going to leave a maximum amount of pressure. That said, at 28 degrees Celsius, what is that partial pressure of water, or what's the vapor pressure, class?
3.7.
3.78 kilopascals. There's really not that much pressure, right? Now, normal atmospheric pressure at this particular location is 101.4 kilopascals. But inside the bottle, there's got to be 101.4 kilopascals of pressure, but some of that is vapor. The rest of it is the oxygen itself. So if we just subtract the vapor pressure from the given pressure, it'll give us the actual pressure of the gas. What do we get when we subtract there, Olivia?
97.62 kilopascals.
This is the oxygen's pressure, right? This is the pressure of the O2 gas. Vapor pressure 3.78, oxygen's partial pressure 97.62. There's the total pressure 101.4. Do we remember doing that first step? That's the only little kink in the works, is when there's vapor pressure to be accounted for, to subtract it from the total pressure. And now there's the pressure. We know the volume is going to be the 0.64 liters, and we know the temperatures. Now it says 28 degrees Celsius, but we don't use Celsius, class. We've got to have Kelvin, so let's add it to 273.15 to get. So there's our pressure, there's our volume, there's our temperature. Of course, we know R, class, is 8.314 liters times kilopascals over Kelvin times moles. And we just got to find the number of moles. Nice thing is, we don't even want us to find grams or anything weird like that. It's literally just how many moles. So we're going to plug it into the ideal gas law, which is, class? I would strongly suggest start by writing it and then show how you're going to get the N by itself. How do I get the N all by itself, class? Divide the R and the T. So it's going to give us PV over RT. We'll plug in the pressure, which of the oxygen is the 97.62. The volume is the 0.64 liters. The R is the 8.314. The temperature is the 301.15. And then as a reminder, when you type it into the calculator, either this times this divided by, and then put parentheses around this, or this times this, there's a decimal there by the way, divided by this, and then divided again by that. Just a suggestion is to divide them separately. Plug it into the calculator. And how many moles are we going to get? It's a really small number. It's tiny. What did you have, Olivia, for the number of moles?
This is
Okay.
0.02.
0.02? Okay, only one sig fig? Oh, yeah. Remember, the first zero is not significant. So 0.2, did you have a longer number written? That's all you have was a 0.02. Tyler's got something?
0.024876.
Okay, 0.02 and 48. So we're at 0.025. Is it 2? Yeah, 2 sig figs. So 0.025 moles of oxygen. All right, anyone else get that same number, the 0.025 that they got? Yes, no, shake or rattle? Okay, good. All right, Nick's finishing up. You good to go? All right, questions on this problem? All right, now let's move into stuff that we talked about more recently, because that goes way back to the section 5.2, section 5.3. Let's get into chapter 6 finally. And have your books available, page 112, table 6.1, you're going to need it. We've got C3H8, which I believe is propane, reacting with oxygen, so it's a combustion reaction, and it's producing steam or water vapor and carbon dioxide gas. And we're trying to figure out what is the enthalpy of reaction, and is this exothermic or endothermic? Well, if it's a combustion reaction, class, it's going to be what kind of reaction? It's gonna be exothermic, and it's probably gonna be a really, really big exothermic number. By the way, is exothermic positive or negative delta H? It's gonna be a negative delta H. So we're expecting negative something, and it's probably gonna be hundreds or even thousands. That's our anticipation. So we go back to page 112, table 6.1. What is propane's enthalpy of formation?
Negative 103.8.
Negative 102.8.
103.
Negative 103.8. All right, so we have negative 103.8. That's enthalpy of formation for carbon and hydrogen to come together and make propane. Plus, we have oxygen. Well, oxygen's an element. In the standard state, what is the enthalpy of formation for any element, class? Zero. The elements. And then I said also let's add in an X. Just a value to hold the enthalpy that's going to be accounted for here. We have 3 carbon dioxide. So we're going to have to multiply whatever carbon dioxide is times 3. What is that from the chart?
Negative 393.5.
All right, plus we have 4. Now it's not liquid water, it's gaseous water, so it's a little bit different number. So it's not the negative 285, I think it's the negative 241. Find gaseous water or steam on your chart.
Negative 241.8.
Negative 241.8, that's what it is. Okay, just remember, I felt like I remembered 241. But remember, we're going to have to multiply these by 4 and by 3 because we have 3 moles of carbon dioxide being produced, 4 moles of steam being produced. From here, you just do the math. You multiply the 3, you multiply the 4, you add those big old negatives together to get a really big negative. We don't worry too much about the plus 0. This is going to migrate over and it's going to become a positive. So whenever we get really massive negative, we're going to sneak a little bit of positive into it. It's not going to do much. And so our delta H, our enthalpy of reaction, is, yes, going to be that really big negative we expected to get. Negative what? What did you get, Olivia?
Negative 2,043.9 joules.
I think it's kilojoules, if I'm not mistaken. Did you get that as well? You're all typing it in still. That sounds about right. Negative 2,000.
I think I did something wrong in mine because I had to go back and messed up when I was typing something.
All right, I got a nod from Nick on that. Do you know how to do it tomorrow? You feel comfortable doing it tomorrow? All right. Questions on finding enthalpy of reaction based on enthalpies of formation. Any questions on that? People still typing? And again, since it's a negative delta H class, that tells us it is exothermic. Are we ready to move on to the next one? Getting some nods. Good. All right, moving on to the next one. We have iron and water, and that creates rust and releases some hydrogen gas. So 2 moles of solid iron plus 3 moles of liquid water producing iron oxide in its solid state and 3 moles of hydrogen gas. Well, again, anytime there's an element class, at standard state, the enthalpy of formation is 0 joules. So forget the iron and forget the hydrogen. So really it's just 3 times water, which, let me use that one enough. I think it's negative 285.8 plus something. And then I don't have that one memorized. Iron oxide. What is solid iron oxide's enthalpy of formation? You can go ahead, Olivia.
Negative 824.2.
All right, somebody else like that number, negative 824.2? All right, so pretty straightforward. We're going to multiply by 3, and then whatever it is, we're going to add it to the other side. So what is 3 times negative 285.8? But we're going to move it over to positive 857.4. And so our change in enthalpy is going to be the positive 857.4 plus that negative 824.2. It's going to be like 30 something, 33.2 kilojoules. By the way, it's positive. Positive delta H, positive change in enthalpy tells me it's endothermic because there's absorbing energy into the reactants more so than releasing them into the products. So absorbing energy in endothermic reaction. The next one, a system released 735 joules of heat into its surroundings as it did 975 joules of work on the surroundings. Finding the change in internal energy. What letter do we use for energy, class? Internal energy. Delta E. Energy changes, delta E. And we said that energy changes cannot be, you can't see energy directly, but you can calculate energy changes based on two things. What caused changes in internal energy? Heat and work. There we go. We use the two words, right? This much heat, this much work. And so we just plug in the numbers. Now if it receives heat, class, is that positive or negative? That's positive, right? So you receive money, that's a good day, that's a positive day. So positive 3.4 kilojoules. And then the surroundings do work on the system. If they're doing work on the system, wait, I'm on the wrong one, I'm on number 6. Let's try number 5, shall we? Number 5. Okay, it releases 735 joules of heat. Is that positive or negative, class? That's negative. So negative 735 joules. And it did 975 joules of work. If you do work, are you gaining or losing energy? If you do, I mean, picture raking the yard or whatever, right? You do work, you do exercise, kind of working out, right? You do exercise, you are losing energy. So that's also negative 975 joules. Well, that's a lot of work, that's a lot of heat out, that's a lot of work out. So that's going to be a pretty negative drop in internal energy we get. There we go, and big time change in negative, right? The next problem says it receives, here's the one I was looking at, 3.4 kilojoules. Positive or negative? That's positive. Receives 3.4 kilojoules of heat. And the surroundings do work on the system. If somebody does work for you, is that positive or negative? That's positive, right? It's gaining the benefit of the work. It's not expending its own internal energy to do work. It's receiving work. So that's a positive 6.7 kilojoules. Once again, we simply add them. And I don't think I meant to have two problems on here where they were both going the same direction. What if it had done the 6.7 kilojoules? Then it would be negative, and you'd have a positive 3.4, negative 6.7. Anyway, so what is that, 10.1 kilojoules? Positive 10.1 kilojoules change in internal energy. Questions on those energy changes? All right, Nick, you got to read the next one for us.
Nick has a mug with 375 grams of water at 22 degrees Celsius. He wants to make himself some green tea, but needs to raise the temperature of water to 85 degrees. How much heat must be added to the water to raise its temperature?
Do you like green tea?
No.
Me neither. I wasn't sure who to stick with the green tea, so Nick it was. All right, so you want to raise the temperature of the water. Well, in order to raise something's temperature, class, you've got to add heat, right? How do we find heat? Q equals C sub SP, M delta T. And we just plug in the numbers. Now, it's water he's trying to heat, so the specific heat of water, class, 4.1. And it said that on the problem, so you didn't technically have to look it up. You didn't technically have to remember it, but you probably did. What mass do we have here, Nick?
275.
He must be really sick. He's making a big old mug of tea. That's a lot of tea. And you're trying to raise the temperature. Remember, anytime there's a temperature change, class, it's what minus what? Final minus initial. So the final temperature you want the water to be to properly steep your tea, sir, is what?
Final is 85 degrees.
But the initial temperature was
22.
22, so final minus initial we get a change of?
63.
Good, 63 degrees. We just multiply the numbers together. The 63 times the 375 times the 4.18. You get a really big number. It takes a lot of heat. Fortunately, the microwave can provide that energy there. And what is the heat that must be added to get your water up to the proper temperature? As he plugs it into his calculator. Olivia, what did you get when you worked it the other night?
The exact number was 98,752.5.
All right, and then you rounded to, I'm guessing, 2 sig figs, right? And you got 99,000 joules. Or if we wanted to, we could take a shortcut on the 1,000 and just say 99 kilojoules. Either one's fine. You don't have to switch it to kilojoules necessarily. But if you see the 99,000, you're like, I'm too lazy to write 3 zeros and a comma. Let me throw a K on there instead. That would be fine as well. Grace, question.
And for this one, we don't have to change the Celsius to Kelvin.
No. Okay, so remember in the gas laws, PV equals nRT. This is a really good point to bring up. Temperature has to be in Kelvin. In the heat formula, because the specific heat is listed as joules per gram times degrees Celsius, we want degrees Celsius. So for the heat equation, great question, degrees Celsius. For the gas law, Kelvin.
Okay.
Great question. Glad you asked. All right, other questions? All right. Okay, Grace, you get the next one. Number 8, read it for us.
During the lab, Grace heats a 45-gram piece of aluminum to 124 degrees Celsius. He then drops the piece.
Okay, so I will confess, I stole this from a physical science review question because we were talking about the same thing, and it was a guy in the lab before. Read she right there.
She then drops the piece of aluminum into a calorimeter containing 150 grams of water that is 25 degrees Celsius. After the system reaches equilibrium, the water temperature is 31 degrees Celsius. Based on this data, what is the specific heat of aluminum?
All right. So we've got a piece of aluminum, but we also have some water. We got two things being discussed. One of them is going to be losing heat, right? The really hot aluminum, plop, into the water, and it starts cooling down. The water, nice and cool before, starts warming up. Here we need to use what formula? Grace?
Q loss equals Q gain.
Close?
Negative Q loss.
There we go. Negative Q lost equals Q gain. But in place of Q, we still use the heat formula, which is, class? There we go. CSVM delta T. So we're just plugging it in twice. Once on the heat, on the loss side, once on the gain side. Obviously, what is losing heat here, Grace?
The aluminum.
The random piece of aluminum that we don't even know what it is. It's just something made of aluminum. So the aluminum is on the losing side, and obviously gaining the heat is the water. All right, so we don't know the specific heat of aluminum. We could look it up, but we're trying to see how accurate we are with our number and our measurements here. So we're going to calculate the specific heat. The mass of the aluminum.
45.
All right, now for the temperature change. Remember, class, temperature change is always?
Final minus initial.
All right, so the final temperature of the aluminum is what, Grace?
31.
Good. When it talks about equilibrium, equilibrium is the final temperature. So 31 minus whatever the aluminum started at.
124.
Right, so if we have 31 minus 124, that's going to give us a negative delta T. Well, of course, it's losing heat. So we're going to have
Negative 93.
negative 93. Conveniently, the whole reason we have the negative in the front is purposely to cancel with that negative. They cancel, and now we're back to positives, which is happy. On the other side, we got the water, and from the previous problem, we know the specific heat is
4.9.
the mass of the water,
150.
150 grams. All right, and then again, its temperature change, still final minus initial. Final,
Is 31.
good, it's final for both, right? Equilibrium means it's the final for both things, minus the initial for the water.
25.
It's just a change of
6.
6 degrees, so that's not too bad at all. We can multiply all of these together, get a really big number. Multiply these two together, and multiply by the CSV to get a little smaller number, probably. I don't know, it might not be smaller. And we're going to divide both sides by whatever this number is. And that'll give us our specific heat. While they're typing it in, what did you get, Olivia?
0.8989.
All right, and then how many sig figs? That is correct, by the way. How many sig figs?
It's 2, but I was confused on how.
Yeah, so we're going to cut it here, but 8 would have to bump the 9 up to a
0.
10, which means we write the 0, and that carries the 1 to give us
90.
0.90. And since there's a decimal, this 0 is significant. So there's our 2 sig figs, and there are units for specific heat, joules per gram times degrees Celsius. And there it is. All right, the rest of you typing it in, make sure you get the 0.8989, blah, blah, blah. Getting a nod from a few people. Questions on this law of heat exchange? Nick, good to go on this? And you missed well, I think you were here for most of this. It was the next problem that you missed all of. All right, so let's take a look at problem number 9. And let's see. We've got everybody else in the back row, so Abigail, your turn. Go and read number 9 for us.
Wait, I have a question on the last one.
Yes, ma'am.
For the CSP, what did you plug in for
The aluminum?
the water?
The water is 4.18. The previous problem up here said that specific heated water was 4.18, so we just kind of assumed we could bring it down.
So if we don't have the other one, that's what we would do.
Right, well, we were finding aluminum, right? So that's why we left this as C sub SP, and we were told in the previous problem that water was 4.18. Does that answer the question? All right, good. Any other questions on this before I erase? All right, now Abigail, read number 9 for us.
27 gram ice cube at negative 14 degrees Celsius is taken from a freezer and put into an insulated cup. After a while, the cup holds 27 grams of water at 23 degrees Celsius. How much heat did the ice cube absorb?
All right, so we've got ice cube at negative 14 degrees Celsius. Eventually, it's going to become water at 23 degrees Celsius. Two things have to change, class. We have to change the temperature. It's got to go from negative 14 to 23, but we're also having to change the state. It's going to turn from ice to water. Where does ice turn to water? At 0 degrees Celsius. Because at 0 degrees, you can have ice or you can have water, can't you? So to go from ice at negative 14 to ice at 0, class, that's a temperature change. To go from 0 water to 23 water, that's a temperature change. But to go from 0 degree ice to 0 degree water, we're not changing the temperature. This is where we're changing this is where we're going to need what kind of heat? Latent heat, specifically of fusion, right? Because we're melting this substance. So temperature changes, we're back to CSPM delta T. We're going to have 2 of those. But at the state change, Q equals specifically sub FUS heat of fusion. All right, so the mass was 27 grams. Is that correct, Abigail?
Yes.
Okay. And then ice's specific heat was the 2.10. The mass, 27 grams. What does the temperature need to change to go from a negative 14 to 0? Again, we're not trying to jump all the way to 23, just negative 14 to 0. 14 degrees. And we're going to multiply all those together and get, I don't know, 600 or 700-ish?
793.8.
Oh, that was closer to 8. So 793? We like that number? 793.8? Is that what I heard? All right. Yes, ma'am.
Do your sig figs matter here, or
In the final answer, yes. But we're not until we get to the final. All right, let's do the other temperature change while we're on a roll. We now have water. So we know the specific heat of water, class. 4.18. The mass, it's still 27 grams. It's just not an ice cube anymore. And the temperature change. To go from 0 degrees to 23 degrees, what's the temperature change? 23. And so we're going to multiply those numbers. Oh, I don't know. Somewhere around 3,000 maybe? 2,000 something-ish?
2,595.78.
0.78. We like that? Okay, so not quite as high as I was expecting. I was expecting a little higher in the 2000s. All right, now for the phase change, the state change. We're going to multiply the mass, which is still 27 gram ice cube, but we have to melt all 27 grams of ice. And we said the heat of fusion for water is joules per gram, so we're multiplying by the 27 grams. Okay, I'm done guessing. What is it? 9,000. Oh, 9018, 9018. All right, so what do we got to do? Add all these answers together to get the total heat it takes. 793.8 to get it to the melting point. 9,018 to actually melt it. 2,595.78 to raise it up to room temperature. So total heat required, what did you have, Olivia?
12,407.58 joules.
All right, and then sig figs, looks like 2. So really rounded number. 12,000 joules rounded, or 12 kilojoules if you don't want to write all the zeros. All right, the rest of us have that. Question, Olivia?
So would we go by the sig figs in the addition?
In the well, sig figs in the original, because technically, if we were going along, we would round to 2 sig figs everywhere. We just go back to the original problem when we round 2 sig figs, because when we say it's a 27 gram ice cube, is that exactly 27? It's probably best guess 27, right? So that's where we're going to have to round. Around 12,000 joules gives us our rough answer. All right, so we literally have no time at all for terms, but at least we got through the math. Okay, so I'll put this up if you want to rewatch the math and obviously the terms. Separate video. I hate that for you. I'm sorry. Wish we could have done the test Wednesday. We just didn't work. Only homework is to study, and then Nick, make sure we get the getting started worksheet done. And I forgot to turn off the video. All right.
I felt like I did 3 problems.